Hi, everyone. I want to solve one example and say a few words about eigenvalues and eigenvectors. We are going to deal with them in this couple of days, so maybe one extra example is not going to harm anyone. So I'll start with setting up an equation. Everyone remembers that we can multiply matrix by a vector. Well, matrix A, let me just give you like general shape, is going to look like this. Let's say matrix n by n. Okay, and over here n square matrix. Sorry, a vector x. X is going to look like x1, x2, xn over here, and vector b looks like b1 and bn over here, right? Well, this is just a standard non-homogeneous equation for matrix A. And we are searching for a solution X, which is going to be multiplied by this matrix and give us vector B. Sometimes, in some rare cases, vector B is going to be proportional to the vector x itself. Proportional means that it's going to be actually equal, vector b is going to be equal lambda vector x. Again, it's not going to happen all the time, but sometimes if you kind of look for something special, let's say, so equation can be modified into equation matrix A multiplied by vector x equals lambda vector x. Well, of course, it's not going to happen very often, like when you take a vector multiplied by a matrix and get the vector itself, right? So basically, guys, in these rare cases, we are going to have like fingerprints of the matrix. And we call these rare cases, like the vectors are called eigenvectors, and the values which are sitting in front of them, like the coefficient of proportionality, are called eigenvalues. Okay, I'm going to solve, I did solve the equation similar to this in lecture, but I want to try it one more time, just kind of to go maybe more deep into steps. So how do we solve this equation? What is unknown here and what is known here? Known is A. Unknowns are, let me kind of underline them. Unknowns are vector x and the value lambda. So basically here we solve two problems, one problem on lambda and one problem on x. And we have to solve lambda first. So how I'm going to solve it? I'm going to move everything to the left side. Let me change my color. I don't want to write down in red. So I'm going to put matrix A multiplied by vector x minus lambda multiplied by vector x equals to 0. Here, 0 is not just our regular 0, like a number 0. It's actually a vector 0, right? Because we have vector here, and 0 is going to be a vector 2. Sorry, I'm using Zoom whiteboard and it gives me lots of touching points over here. So now I want to take x, vector x, outside of parentheses. So when I do this for this product, I'm going to just have matrix A, right? Here, I do not have matrix. Actually, lambda is just a number, just a real number. So if I take x outside of here, I'm going to be left with a number, which is not very good, actually, because I cannot subtract number from a matrix. I'm supposed to subtract matrix from a matrix. So what I'm going to do to avoid this difficulty when I'm modifying equation, I'm going to represent this product as lambda I multiplied by vector x. What is I? I is identity matrix. I'm going to write it down. So in this case, it's n by n matrix, which has ones on diagonals, and everything else is 0. So 0 here, and ones are sitting here. If I multiply identity matrix by vector x, I'm going to get the very same vector x. That's a like point of identity matrix. It's not modifying. It's like a 1 for real numbers. You multiply 1 by any number, you get the same number. So that's why I can do this. It's going to make my life a little bit easier when I take away x outside of parentheses minus lambda I And over here, I'm going to have vector x and equals to vector 0. What we have over here, it's a homogeneous equation. And we remember from my lecture that homogeneous equation has only two options. Either have only trivial solution. Trivial solution is x equals 0 vector, which is always here, but like not very interesting. That's why we call it trivial solution. Or it can have a non-trivial solution where x is not equal to 0. But usually this non-trivial solution does not happen like as a unique solution. It's going to be like infinitely many of them. So what do we supposed to have to get this non-trivial solution? We're supposed to have determinant of the matrix which sits in front of x to be equal to 0. So determinant of the matrix A minus lambda I must be equal to 0. And here, this 0 is just a regular 0, like we deal with like real numbers, right? This is determinant of the matrix. We remember that determinant is just a real number. So if you kind of take a determinant of the matrix, you are going to have like product of some terms in the matrix, right? For us, it's going to mean that we have equation about lambda because you do know all numbers for A, you do know all numbers for I, which are ones, right? And you do not know only lambda. And for us, it's going to look like a determinant of the matrix, which is going to look like this. A11 minus lambda. And then over here, A12 and all the other terms. So you basically are going to subtract lambda on diagonal. A22 minus lambda and like the other elements are going to stay same. And of course, when you calculate this determinant, you are going to get a polynomial. You add them up, you kind of there are just n lambdas, and that's going to be polynomial of nth degree. And of course, it's going to have some solutions. And these solutions are going to be our eigenvalues. Well, these eigenvalues are going to be specific for the matrix. And basically, after we find these eigenvalues, we can plug them in over here into our equation over here, sorry, and then calculate axes which correspond to every eigenvalue. So one like normally we expect to have n eigenvectors as well as n eigenvalues. There are some features like, sometimes you solve polynomial and you get multiple roots. You also can not necessarily have real roots, right? You can have also lambda, they can be real or complex numbers. Usually we do cover this very deeply in linear algebra class. So for right now, we're not going to dig too much into like multiple solutions and other stuff. We are going to try solve simple cases, right? So what I'm going to do, guys, I'm going to consider one example of just the matrix and like steps which we are using to solve it. Again, here we are not solving differential equation, we are solving algebraic problem. And this is just going to be algebraic equation. And I think I forgot to close parentheses. Here I started and here I closed it. This is number one, I'm going to round it up, or number two. It's gonna look better a little bit. So we don't look for this solution. It's always there and we always have it, but we do look for some non-trivial solution. Okay, so I'm going to consider a matrix. Let me just move to a different screen so I have like whole problem on the board. So I'm going to consider matrix A, which is 5, -1, 3, and 1. And I'm going to search for eigenvalues and eigenvectors of this matrix. Again, we need it because when we solve differential equation, we are ending up with a very similar problem. That's the reason why we're trying to deal with it. So first, I'm going to write down number one, look for lambda. How? I'm going to set up determinant of A minus lambda I. In our case, it's going to be what? It's going to be 5 minus lambda. I'm taking lambda away from diagonal elements only. 1 minus lambda. And in 2 by 2 case, you know, determinant is easy to calculate. And in our case, that's going to be what? 5 minus lambda, 1 minus lambda plus 3, right? We multiply these diagonal terms and minus 3 by -1, which is plus 3 equals 2, 0. We're setting up determinant to 0. And what we have, it's just equation lambda square. I simplified the terms. Maybe I did it wrong, but I'm hoping that I did not do any mistakes. So I got just quadratic equation, which is going to have two solutions. Lambda 1 equals 4 and lambda 2 equals 2. Let me just double check if my solutions are correct. So give me a second. So lambda minus 4 minus 2 multiplied is 8, and minus 4 minus 2 added is 6. Yeah, looks like we do have correct solutions for lambda. And now we are going to look for eigenvectors again, because our goal is to find them. So usually that's going to be number 2, eigenvectors. And because we do have 2 lambdas, we are going to find eigenvectors for each lambda separately. So we are going to start with lambda 1 equals 4. So again, I'm returning back to my equation a minus lambda I multiplied by x equals to 0. Now, what is good? I do know lambda already, right? My lambda actually is equal to 4. So actually what I have, a minus 4i multiplied by x equals to 0. And I have only one unknown, x. Well, I'm going to put actually this 4 into my matrix, a minus lambda I, and try to solve it just literally like equation. So what I'm going to have? Well, I have 5 minus 4. Here I have minus 1, right? I'm just plugging in 4 over here, and 3 and 1 minus 4. And I'll need to multiply to my unknown vector x1, x2, and supposed to get 0, 0 over here. I'm trying to write it down in a form, in a shape, like very close to the system of equations, how we used to solve it. So let me modify it a little bit, simplify, let's say, and I'm going to have equation 1 minus 1, 3 minus 3, multiplied by vector of unknowns x1 equals to 0, 0. Guys, do you see that these two equations, the first one and the second one, are just multiples of each other, right? You multiply this by 3 and you get this one. So that's normal, right? Because in other case, we are not going to find non-trivial solution. And how we did this? We found lambda, which is going to turn actually this matrix into linearly dependent rows. So when you have this, when you have like extra equation, which really brings no information into the system, you are going to have at least one parameter here. So you can choose either x1 or x2 to be a parameter and solve for the other variable. I'm going to choose, for example, I'm going to choose x2 to be a parameter. My x2 equals to parameter. I'm going to write down here parameter. And parameter means any real number. Now I'm going to write down the first equation. You can write down the second equation. It's not going to make any difference. So I have equation x1 minus x2 equals to 0. I'm going to plug in this t, and I'm going to have x1 minus t equals to 0, from where x1 equals to t. So my solution, my solution vector, which is x1, x2, is going to look like this, t and another t. Well, again, what is t here? T is a real number, any real number. Well, what I'm going to do, guys, because t and t are just the same t over here, I'm going to take it outside of the vector. And I'm going to have 1 and 1 over here. And t is going to be just arbitrary constant. Now, maybe I'm going to call it actually arbitrary constant, not t, because we like to use constant in differential equations, right? So I'm going to write down that's C1, 1, 1. So that's going to be my first solution. Now I'm just going to repeat the procedure for the second solution. Damn, I don't like that I have this touches. I don't know why. Okay, so I'm going to do lambda 2 equals 2, and I'm going to repeat everything, but I'm going to skip some steps. I already kind of, explained everything. So I'm going to have 5 minus 2 over here, minus 1, 3, 1, minus 2, and over here is going to be x1, x2 equals to 0, 0. And well, what I'm going to have if I simplify, that's 3 minus 1, and that's 3 minus 1 again. And that's normal because again, otherwise we are not going to have determinant equals to 0 and non-trivial solution, right? They're supposed to be linearly dependent to give us non-trivial solution. Now, I'm sorry. Which one are we going to solve? Again, you can solve first equation or second equation. It does not matter. I'm going to set up again x2 equals to t and then try to solve the first equation. So the first equation is 3x1 minus x2 equals to 0. If I plug in t, it's 3x1 minus t equals to 0. And x1 from here equals t over 3. Perfect. Now I'm going to write down my solution. So the next one, you guys, I should label this as x1 because it corresponds to lambda 1, right? I'm going to label this one x2 and to write down, so it's t over 3, and over here is t. Now I'm going to repeat the same procedure. I take t outside, and I'm going to have 1 over 3 and 1. Actually, I don't like to have fractions because t is any real number. Same, t is any real number. What I can do, I can multiply everything by 3. And that's going to give me, again, t. If I multiply everything by 3, it's going to give me, instead of 1 over 3, just 1. Sorry. And instead of 1, it's going to give me 3. I just don't want to have fractions, otherwise I'm kind of happy with this. Well, and of course, because I don't like to have general parameter t, I want to have a constant, and I'm going to use a different name for the constant just to make a difference between this constant and that constant, because these are two independent constants. I have another eigenvector. Of course, the vector itself is 1, 1, right? But you can stretch it and multiply it by any constant is going to just increase the size or decrease the size of the vector. So I found two eigenvalues, and I'm going to write it down. Lambda 1 equals 4, and x1 equals c1, 1, 1, and lambda 2 equals 2, and x2 equals c2, 1, 3. Well, that's my final answer for this problem. Normally, for differential equations, we'll need to go a little bit further. We'll need to combine it into general solution. But here, the question was only find eigenvectors. Let me write it down. Find all eigenvectors and eigenvalues. Okay, so we are going to repeat this procedure for like some other problems in this chapter 7. So makes sense to kind of understand what we are doing. Yeah, usually I'm not going to go beyond the matrix 3 by 3 because you know that even solving this simple problem took us about like 10 minutes, right? So bigger matrices, longer time to do it. But I want you to understand ideas of how to solve using these matrices. Okay. Well, that's all for this problem. I'm going to post the video and notes just like right now.